Okay, good morning. And today is our first class for teachings. And the topic related today is chapter 1. As I mentioned before, we have the quiz, and the first part is start from the chapter 1 to chapter 3. And I think the chapter 1 is very simple, and some just try to highlight some important ideas associated with the fluid mechanics. So today totally we only have the 32 pages slide, and so it's a first class, so I will try to speak very slow, and for you better understand what I mean in class. Okay, so the title for the chapter 1 is Building a Solid Foundations. And usually we in the following class we will see some engineering problems. Okay, and then when we have the problems and we try to figure out which technology can help me to find the solution for the problems. And then you apply some technology to have the solutions, but you don't have the knowledge to identify which one is the better one. So that's why the reason you sit here, and I will try to teach you some knowledge associated with the fluid mechanics. So after you know the background knowledge for the fluid mechanism and you meet the problem, you found the solutions, and you have the knowledge to identify which one is the best. Okay, so the second slide, I just summarize all learning outcomes for these chapters. And during the class, you will know sometimes I teach you the knowledge associated with the fluid mechanics. But the problem we meet is engineering. So before we learning the knowledge, we should understand the certain definitions of the engineering first, and then what is the fluid mechanics. So I will provide the definitions of two important words in our class later. And then, as you know, the major topic in this class is our target is the fluid. So I need to tell you how can we define the fluid materials in the class. As we know already, there are three types of the materials: the solid, liquid, and the gas. So how can we distinguish each other? So I need to base on the material behaviors first. And we can base on the different ideas. As you can see, we have the macroscopic or the macroscopic approaches. So different idea, different material size, you will have a different definition to help us to distinguish the different materials. And then when we discuss the material, sometimes we will use the physical properties. So as I show in here, some physical properties like the density or the specific weight can help us to identify different materials. But when we discuss the different material with the physical properties, we should satisfy some assumptions. And one of most important assumptions is we call that the continuum assumptions. And later I will tell you why and the major ideas for the continuum assumptions here. Okay? And then only one equation in this chapter, we call that the ideal gas law. And the ideal gas law is very older equations when we are a junior or junior high school. It's a long time ago, so we already studied the ideal gas law in chemistry class. So, but it is only one example and the equation I will teach you in this class. But the idea is I want to tell you the reason why we can use the ideal gas law. So sometimes you under some conditions and you can say the gas is ideal gas. If not, you cannot apply the ideal gas law. And we call that is a real gas in here. Okay? And if you apply the ideal gas law, you will know some relation between the pressure, temperature, and the density and the mole mass. Okay, as I highlight some physical properties here, and when we apply the ideal gas law, we will know the relationship between each other. And the final one, because there are many engineering approach. So in these chapters, we will show one example. We call that the critical thinking. And how can we apply the critical thinking to solving the problem for the engineering? Okay, and when we apply the engineering approach, and for our problems, we should know how many physical property we will use. And for each physical properties, what's the units we have? And we will use some equation to find out our problem solutions. And based on the equations, how can we do the dimensional homogeneous problems? Because the equation maybe include the density, include the velocity, but we know the density and the velocity has the different units. And based on the equation, how can we do the dimensional homogeneous analysis for our problems? Okay, so that's just learning outcomes in these chapters. Okay, if in the following slide, I will go in details for each part. And you will know what are the major idea and the knowledge in these chapters. So the slides, I put the very big words for our on the top. It's engineering, mechanics, and the fluid. This is before we teaching the background knowledges, and we should interpret before the certain definitions of the engineering and the mechanics and the fluid. So what's the engineering? The engineering usually be used by solving problems by we will have the innovating and the designing and the applying and improve the technology. So again, we have the innovating. What are the innovating first? Because we have some innovating ideas. But based on the idea, we should design your device or your methods or your approach. And the third part, we apply the method we designed. But after you apply to the real case, you will meet some problems. So you should improve some things. And the do loop, like the innovating, designing, applying, and improving, this is we should do the try to do the do loop and repeatedly do the loop until you receive the best solutions. Okay, so this is the engineering defined. So usually just innovating, designing, applying, and improving. And then what's the engineering methods? So we have many methods, but the idea is such as the critical thinking is an engineering approach. We should have some critical thinking and how to run the loop. And sometimes we should build out the math model. We should build out a math model to identify our question and found the solution for our problems. Okay, so this is just engineering. And what's the mechanics? The mechanism is deal with the motion and with the force that produce the motions. And we call that the mechanics. So mechanics can divide it into two fields. The one is the solid mechanics, but in our class is the fluid mechanics. So it's a difference because we will have a different target. So the final one is the fluid target in our class. So what's the fluid? The fluid, the certain definition is the material can continuously deform under the actions of the shear stress. So I apply the shear stress to one material, and I can see the material response. And I see the material response just the flow, or just didn't broken or didn't failure. And we can say that the material is fluid, like the liquid or the gas. You push the shear stress and the fluid will start to flow. But if you apply the shear stress on the solid, like the table, maybe the table will broken. Not didn't flow, just broken and the deformations. Okay, so when we define the fluid, we will say that the fluid material under the shear stress will continuous deformations. Okay, will have the continuous deformations, didn't broken. Okay, so I just highlight one interesting the engineering systems like the figure showing here. As we know, the figure in here is a skydiving exercise. Okay, so as I mentioned, the engineering we design, we have an innovating idea. Like the skydiving exercise is a very crazy exercise, right? So we need to design what's the systems and why the people can floating on the air. And after we design it and we try, so we apply. And during the apply, maybe the people will falling down and die. Okay, so in that case, we should improve some ideas. Maybe something wrong in our systems. Okay, so I just highlight some important ideas on the right-hand side. And we can figure out by the movies. As you can see, that's the skydiving exercise. And when we see the movies, we will try to thinking how many forces in these systems. Because this is an engineering design problem, right? And how many forces in the systems. So first, if we don't have the background knowledge, I will say the first force should be the lift force, because the body will lift on the air. So the first force should be the lift force. And the second force is the drag force, because we have some resistant force caused by the air. So we have very important two forces involved in this system. First is the lift force, and the second is the drag force. And when we are looking into more details, we know that some air floating pass through our face and the body. And in the fluid mechanism, very important force is, we call that the viscosity force. The viscosity force, like the solid mechanism, we call that the friction force. But for the fluid, we call that is the viscous force. Okay, so there are some viscous force just caused by the air floating on the face and on the bodies. So we have some viscous force. And the viscous force usually acting along the boundaries to different phases. like the gas and the liquid, there is the interface boundary. And the friction, like the solid friction force also acting on the two block boundaries. Okay, so again, we can see the movie, so we know that the air floating through the face and the body will have the viscous force. And another force is, we call that the buoyant force. And the buoyant force is caused by, you can see we have some inflated parachutes. Okay, we have the inflated parachutes to provide the buoyant force to suspend the body. So if we don't have the parachutes here, and why the parachute design the inflated, that will provided the maximum buoyant force by the shape of the parachute. Okay, so we just based on the movie, and we know that the very dangerous exercise, but we should be carefully to design the systems. And totally the system involves the four forces. As I mentioned, we have a lift and the drag force. And the third force, we call that the viscous force. Viscous force is similar to the friction force, but applied a different material. In fluid, we call that the viscous force. Okay, so in solid material, we call that the friction force. Okay, so the definition difference. And finally is the buoyant force. It's caused by the parachutes. Okay, if you don't have the parachute, you don't have the buoyant force, you will falling down very quickly. So the parachute can help you to adjust the height in your bodies. And you can see some words I just put here, because the lift and the drag force is associated in the chapter 11, which is out of the range in our teaching plan, because in this class we only teach you the chapter 1 to chapter 8. So I just I will put a little bit ideas for the lift and the drag force during our class. But you can see the buoyant force is associated with the chapter 3, and you will know more details in the following class in the chapter 3. So that's why I put the movie here, because it's very crazy. When we, for the engineering problems, and we meet the problem, we're trying to design. But this is very dangerous. So I cannot missing anything. I need to deeply consider everything, and then I do it. So there is no space to improve, because if something wrong, and the people will die. Okay, so this is I try to put this slide to interpret how important for engineering and the mechanics and the fluid. OK， 那这个可能我停在这里很久，可是我只想跟大家分享说，大家也有可能你已经大2、大3，那其实也学了很多力学的课，其实我们还是搞不懂我们 engineering 在做什么。那我刚刚讲的4大原则，其实就是设计、创新设计、应用、改良，就只有这4大问题，这是工程人在做的事，但是不能开玩笑，因为一开玩笑就真的笑不出来。Okay, so the reason why I stay here very lonely, so and I just try to share my ideas for the engineering. Okay, so the first one is critical thinking. Is very famous engineering approach, but nothing special, because you can see this is only the do loop, right? And sometimes we have the problems, and we can also call that is the issues. And I summarize all the issues I have. Then I try to apply some approach, or I build up the some models and do the system test. And after the system test or the models equations, I can provide you some reasons and evidence that support my claim. But my claim should be argued by the people with the professional knowledge. Like you are a student and you write down your answers, and I'm the teacher, and I will argue you and try to challenge you. Your answer is not correct. So you need to provide me solid reasons and solid evidence to support your answer is true correct, not the wrong. So after that, we repeatedly do that. And then finally, you can make a conclusions. If no any professional people argue your answers, argue your evidence, and totally they accept your claim because your claim is very valid and accurate. So then you can make the conclusions. Okay, so usually in our life, we can apply the critical thinking. We meet the problem because today the weather is so cold, right? So I cannot wake up early. So I didn't attend the class. It makes sense. So you need to support the evidence to teachers, so cold and lower temperature, and the traffic, some problems, so I cannot go here. Okay, and the teacher double check with the Central Weather Bureau's website to check the lower temperature warnings. Okay, it's fine, everything is good. Okay, so you can make a conclusion based on the experiment. In the features, I check the lower temperature and I don't need to attend the class. Okay, so you just support your claim and by some reasons and evidence. Okay, and then right now I'm trying to define the different material type based on the force between the molecules. Between the force, I just discussed the force between the two molecules. So the idea is we based on the microscopic concept because we are looking for very small particles. So the very simple definition, how can we distinguish the different material type? Very easy, because you can see when two molecules are far apart, and we can say there is no force between them. So the material satisfies the ideal gas. But if two molecules are close enough, not very too close, just close enough, and then there is some attractive force, and we cannot say the gas is ideal gas. So we will say that's the real gas, okay? And then if you at a certain distance between the two molecules, we should know that the maximum attractive force between molecules. So we will say that the material is the liquid or solid. So right now we can identify the difference, the ideal gas and the real gas, and the gas or liquid. Based on the table, summarize some ideas. Just compare different conditions between two molecules. So the bottom one, if two curls of the molecules, and then we will have the strong repulsive force. So that's very easy to thinking because if two curls and we will have a repulsive force, that indicates and the two molecules are very difficult to compress because if two curls, they will have a repulsive force. So that's some conclusion here. The liquid and the solid are difficult to compress because the molecules are two curls, and there is a repulsive force between two molecules. So it's very difficult to compress. Okay, So, but until now, we still didn't certainly distinguish the solid and the liquid and the gas. We can only say it's an ideal gas or not. Or we can only say it's a liquid and a gas, or it's a liquid and a solid. So we don't certainly distinguish the different material types if we only based on the force between two molecules. So the next slide, we are trying to use the more detailed physical properties or physical behavior to distinguish the solid and the liquid and the gas. Okay, so there are some very important physical property in the following class we will use is the density. Okay, so for example, if we only based on the physical properties of the density, we can very easily to identify the solid, the liquid, or the gas because the density are quite different between different material types. Okay, and then the next one, we wondering to discuss the different type. Material type has a different response for different effect. Okay, as I highlight two important, the shear stress and the normal stress. In the previous slide, I already tell you how can we define a fluid. So you see the different response for the shear stress can identify the materials type. If we follow solid here, and you can see the shear stress can produce the deformations. But if we focus on the liquid and the gas here, and we know that the shear stress can produce the flow. So it's very different response for a different material type. Not only for the liquid, but also for the gas, where shear stress will produce the flow. But for the normal stress in fluid mechanism, usually we call that the pressure. The pressure is the normal stress. And we apply the normal stress on the solid and liquid and the gas. All of them will produce the deformations and associated with the volume change. So all material, if I apply the normal stress, I provide the pressures on the materials, and they will have some deformations with the volume changes. But the amount of the volume changes will different for different material type. So you can see there is the compressibility properties. What is the compressibility property? It's related to it's easy to compress or not. Okay, so we call that the compressibility. And you can see some bulk modulus in here. You can see the bulk modulus in here, and we have a number. So you can, even though you don't know what the compressibility and what is the bulk modulus, but you know, start from the solid to the gas, the bulk modulus is decreasing. Okay, for the gas, the bulk modulus is quite smaller compared to the solid. So you can try to image out, maybe the small bulk modulus indicate the high compressibility. Because for the gas, it's very easy to compress the gas. But for the solid, it's very difficult to compress. So the bulk modulus indicate the different compressibility effect. Okay? And then, as I mentioned, the viscosity is very important in our fluid mechanics. And you see for the solid, there is the Na. There is the Na. That indicates there is no viscosity in solid material. That's why I emphasize for the solid mechanism, the viscosity effect, we call that the friction effect in the solid material. So there is no viscosity in a solid material. But viscosity of the liquid is higher than the gas. So you can see the liquid is high for the viscosity, and the gas is low for the viscosity. And they are different response for the temperatures. For the liquid, the viscosity decreases as the temperature increases. But for the gas, the viscosity increases as the temperature increases. So they have the different response to the temperature changes. Okay, but the table just quickly summarize some ideas in the table. So in the following class, I will introduce more details and tell you the reason why the different response to the temperatures, especially for the liquid and the gas. Okay, and sometimes I have some Chinese word beside the tables. It helps you to understand what the difference. Okay, so after we have some table summarized and we have highlight some ideas, and the slide just make the conclusions. I just tell you the fluid should be the liquid and the gas. So in our class, we have the two materials we will discuss. The one is liquid and the other is the gas. We also call that is the fluid. And the certain definition is the material can flow freely under the action of the shear stress. Okay, so remember, for the fluid, we apply the shear stress and the material will flow. Material will flow, didn't broken. Okay, you didn't see any water will broken. Okay, the water always the water, and you apply the shear stress, the water try to flow. Okay. And then this is I just highlight one example. If this is our systems for our problems, and this is a steel tank filled with the water and the air. So that indicate we draw the diagram for our system, and we highlight some material we have. Why we need to highlight how many material involved in our system? Because when we discuss some problems and we try to figure out the solutions, and the solution may be associated with the different material have different physical properties, like the air, the gas, and the water, and the tank. They both have different density each other. So we will have some different physical phenomena caused by the different materials. So in the following class, if you meet the problems, and then you should draw the diagrams and highlight how many material you have. And then you should write down the physical property for each materials. And then look your problem and try to figure out which the solution and the model can help you to find the solution. Okay? So, and another important ideas I tell you before, because we should satisfy the continuum assumptions. So this is an example. Because a fluid usually behaves as if it will compress of the continuous matter, and that is infinite divisible into small and small parts. That's because we have the pen, and I can have the half pen and the half pen and half pen, but the pen always the pen. So the physical property of the pen didn't change, right? Even though I broken it, but it's still the pen. But in real case, it's not at all. So that's why we call that the continuous assumption. What is the continuous assumption? As you can see, I have a gas tank in here, and I can capture a small amount of the gas, right? And I trying to measure how many mass and how many volumes when I capture a small amount of the gas. After that, I can compute the density. Okay, so I repeatedly do capture the gas from the tank and repeatedly measure the density so I can make the plot on the right hand side. So what's the plot? The plot is the density as function of the capture volumes. And what's the blue line? The blue line, you can see the density measurement will have some fluctuation when the volume is smaller than delta V1, right? So that indicates if you capture a small volumes, but the physical properties will be unstable. So if you want satisfy the continuum assumptions, your capture volumes should be larger than delta V1, right? So some people will say, okay, so in features, I just capture the big volumes, and I can measure the physical properties. And the physical property can represent all the material I have. But in case your volume is large enough, you will see some incorrect physical property measurement. So that means if you would like to satisfy the continuum assumptions, you can only for some certain volume ranges. If you smaller than delta V1 or larger than delta V2, it's not satisfy the continuum assumptions. Okay, so what are the continuum assumptions? The continuum assumption is indicate your volume, capture volume is large enough. And whether either I capture different volumes during this period, I can measure the same physical property. That means I satisfy the continuous assumptions. Okay, so it's fine. So let's the previous slide just summarized the physical property on the table, but sometimes if your volume material of the volume is quite smaller, you cannot measure the true physical properties. So you can only measure the true physical property during the volume in these ranges. Okay, so what are the ideas? So this is our first exercise. So in the following class for our exercise, usually I will put the answers on the top of the right corner. Okay, so if you cannot follow my calculation in class, you can go back home and recalculate your solution again. And you can check the solution is correct or not. So, and then just make an announcement to you, you should bring your calculators because we will compute some answers on class. Okay, so what's the exercise here? The probability theory shows that including the 1 millionth molecules in the volumes will allow the determinations of the density with the 1% uncertainty. So that's the ideas. We capture the different volumes, and the volume includes the 1 million molecules, and then we will have the 1% uncertainty in measurement the physical property. OK， 所以这个意思就是说，我满足刚才那个假设，我 capture 这个东西，但这个 volume 如果每次都有100万的分子的话，那其实我最后量出来的 physical property 可能会有1% 的误差。也就是说，我密度本来是1000，可是我这样做很多次，可是我可能会有什么1% 误差，不就是有可能会是1010吗？或是980，就是会有1% 的误差。那这个就是从统计或是经验法则里面去做。Okay, so but we have a qubit that contains 1 million molecules should be large enough to accurately estimate the micro properties such as the density and velocity. Okay, so just interpretation for our exercise. And what's the key? We are trying to answer the length of the qubit. So we need to decide the qubit, the size. And then the qubit contains 1 million molecules. And assume we are under the room conditions. And please to calculate for the material, the water, and the air. So right now you only know I capture the water or I capture the air, and I need to decide the cube size, and then I can satisfy the continuum assumptions. OK， 我们刚刚已经说了，如果你的 size 不太正确，其实你就没办法量到一个正确的 physical properties。所以这个问题就想问你说，那我现在已经跟你讲了，我每次 capture 这个气体也好，或者是水也好，那它的分子永远我也确定它是1个100万的数量。那请问你这个 cube size 要怎么设计？因为你要用什么样的容器去抓这个气体，然后抓下来以后，你才去量你想要量的物理量。Okay, so I can try step by step. So the first, I trying to discuss with the water. Okay, and I know the water, the molecules is the H2O, right? So we have the H2O. We have the H2O. And we know that the molar mass, is because the H is a hydrogen, so we know that the molar mass is the 2 because the H is the 1, but we have a 2H, so it's a 2. And the oxygen, we know that is the 16. So totally, we know that we have the 18s, because this is a molar mass. So the unit is the gram per mole. Okay, we know that the 1 mole we have the 18 gram. Okay, this is for the water. And the seconds, we actually know totally we have the 1 million the molecules. So how many more we have? So as you can see, I have provided the 1 mole is equal to the alpha numbers here. If I didn't put the number here, all students maybe forgot 1 mole is equal to the 6.202 and the 23 powers. So I can calculate the mole, how many mole we have right now. Because we have the N is equal to, totally we have the 1 million molecule, right? And we should divide it the 6.02 and the 1023 powers. And you can use your calculator to calculate how many more we have. So I use my calculator to compute the answer. And you can try in your side. So for the number here, I may write down the 0.166. And the power of the 10, we should have the minus 17. Okay, so this is the our mole. So we have the N is equal to this number. So after that, I can calculate how weight of the waters, because I'm trying to calculate the density. Maybe I want to calculate the density, and I already know the density, right? The density for the water, if under the room conditions, I know the density for the water should be around the 1,000. And the unit is a kilogram per meter cubic. Right? The kilograms per meter cubic. Okay. And I know the cubic, how many weight water in the cubic, because I have the molar number. This is the cubic mass, the water. And I have the molar number, right? Molar mass. And I know how many mole I have. So So I can compute how weight of the water in a cube. Okay, so the molar mass in here, we have the 18 grams per mole, and the multiply the mole in here is 0.166, and the 10 minus 17 powers, and the unit is the mole. And after these calculations, I can cancel out the mole, right? And I only have the unit is related to the gram. So use the calculator, and 18 multiply the 0.166, and that will equal to 2.988, and the 10 minus 7 grams. But in our density calculation, the unit we need to have the kilogram. So we should convert the G to kg. So actually, after the conversions, so we know that the mass is 2.99988, and because we should convert the G to kg, so it will equal to the minus 20 power to convert the G to kg. So right now we already have the mass, but what's the unknown parameter? We didn't know the volume, right? We didn't know the volume of the qubit. So that based on the equation of the density, we know the density will equal to the mass divided the volumes. But right now we didn't know the volume. So we can reorganize the equation. The volume will equal to the n and divided the density. Okay, so actually we already have the m, the mass, in here, and we should have keep the unit is the kg, and we're trying to divide the density is the 1000, but the unit is the kg over meter cubit. Okay, so the unit you can also cancel out, and the answers for the volumes is the 2.988, and the power of the 10 changed to the 23, right? Because we divided the 1000 to the density. And the unit right now is the meter cubit. But when we go back to see the questions, we require to find the length, right? We need to the length of the qubit. So we should have the qubit root of the volumes to have the length. So we know that the length of the qubit should be the volume, and I take the qubit root. Okay? So you should have your calculator to compute these answers. And I try to use my calculator to check the answers. Okay, and you can do by your side. Okay, the answers is quite similar. The numbers shown on the right upper corners. Okay, it's the 10 minus 8 meter. Okay, so we finish, and we have the answer in here. Okay, so this is our final answers. Okay, so this is just the ideas. If you certainly know the physical properties you have, like the density, or I already know the density for waters should be the 1000 kilograms per meter cubic. And then I would like to accurately measure the density. So I need to decide how large the containers I have, because I need to satisfy the continuous assumptions. So I can theoretically to calculate how the size of the qubit, the containers. Okay, so this is just a very simple exercise, and when we meet the problem and we have some idea and the assumptions, so you should decide the theoretical answers. Okay, but it's sometimes very difficult. What I means, 我们每次看到这个题目，觉得好像也就是这些数字，可是刚我们看完这个题目，有时候还真的不知道他在问什么。这其实是我们最不会的事情。如果我知道他在问什么的话，我当然就知道怎么算了。但其实我们最难的是，我们根本搞不清楚他要问什么。那刚才这个范例就是说，其实我们先跟你讲了，你必须满足连续体的假设，但是连续体的假设一定会存在一个固定的体积里面。那只有连续体的假设，你才可以不论你的材料忽大忽小，可是你会得到一样的物理条件、物理性质。那所以这时候我们先教了这个，再来看这个题目，才知道哦，原来他想要我们去算这件事情。可是实际上我们通常就是久了以后，10个礼拜以后，我再修这一题给大家看，然后考这一题，那你就会觉得那跟我们这个现在有什么关系这样子？所以我们的重点就是学了就考，你至少知道我们可能要用什么。然后可能要考什么，然后他想要考你的想法是什么。今天没考试啊，不要吓到，我们下礼拜才有考试。OK， 那我们稍微休息一下好不好？这时间也差不多，那我们就10点10分再回来上课。